All right, we have our epidemiology example. We're going to let P of t be the number of people who are sick at time t. And 1,600 is the total population. We have 2 people initially sick, and after 10 days, 100 people in the population have become sick. So the first part, the first thing we need to do is solve the differential equation. This is a first order differential equation, and it is nonlinear because we have a p times a p. That's a p squared, so that's nonlinear. It's a nonlinear differential equation, and it is separable. In particular, it's autonomous, so there's no t's on the right-hand side, so we can separate this. So let's go ahead and solve it. We're going to have a dp over p times 1,600 minus p equals k dt. So we've separated the variables. We need to integrate both sides now, and this integral here is going to require a partial fraction decomposition. So we're going to do this with a partial fraction decomposition. So we want to know what 1 over p minus, times 1,600 minus p is equivalent to when we break that up. So we've got our partial fraction set up now. We want to find an a and b that makes this work. Remember, this is a common denominator problem in reverse. So we multiply through by the common denominator. We get 1 equals a times 1,600 minus p plus b times p. The other terms cancel out on the left-hand side and the right-hand side. We multiply through by the common denominator p times 1,600 minus p. Now pick, this equation has to be true for all values of p, so we pick convenient values. Pick p equals 1,600. That zeroes out the part involving a, and we get b equals 1 over 1,600. If we pick p equals 0, that zeroes out the part with the p in it, and we get a equals 1 over 1,600. So that's nice. Our left-hand side integral is the integral of 1 over 1,600 divided by p plus 1 over 1,600 divided by 1,600 minus p dp. And the right-hand side was just a k dt. So that partial fraction worked out really nicely. Those a and b constants both end up being 1 over 1,600. Can't beat that. Okay, so let's go ahead and do the integration now. So we integrate, we have 1 over 1,600 times the natural log of p plus 1 over 1,600 times the natural log of 1,600 minus p. Looks like I got a sign wrong there on the integration. You need to be careful with that integral. You can do a u substitution, let u equal 1,600 minus p. And on the right-hand side, we have kt plus c, a very simple integration for the right-hand side. Now, this is where things get a little bit ugly algebraically. The first thing I want to do is multiply everything through by 1,600 just to get rid of the fraction. So multiply everything through by 1,600. We have an ln of p minus ln 1,600 minus p equals, I have 1,600 kt plus 1,600 c, and we're just going to relabel this. We're going to call that 1,600 times k our new value of k, and 1,600 times c, we'll call that our new value of c. Those are just constants, so I can change the meaning of the constant as I go, and we typically relabel them using the same letter. It just makes things a little bit simpler, a little bit cleaner. Now, on the left-hand side, a natural log minus another natural log, we can combine those using log rules. That's the natural log of p divided by 1,600 minus p. That's the log rule for subtraction of two logs, and that's necessary here to be able to solve for p eventually. We need that log rule. On the right-hand side, we have a kt plus c. So to get rid of the natural log, we exponentiate. So p over 1600 minus p is e to the kt plus c. We've seen the exponent rules for this before. We know what we're going to do. We're going to relabel the constant c again. E to the c is going to become our new constant c. And now we have just cutting out the middle equations but rewriting what we've already done. This. So that's a solution, but it's implicit. And we can actually solve this for p, and in this case it's nice to do so, even though it's a little bit messy algebraically. So we're going to have c, we're going to multiply both sides by 1600 minus p. So we have 1600 c e to the kt minus p times c e to the kt. I don't want to relabel the 1600c because I have c in both terms now. So I don't want to be changing the meaning of c anymore at this point. Let me put all of the p's on one side. Whoops. Plus p c e to the kt equals 1600 c e to the kt. I can factor a p out on the left-hand side. 1 plus c e to the kt is 1600 c e to the kt. And finally, we have p as a function of t is 1600 c e to the kt divided by 1 plus c e to the kt. Now that's a solution, and we're good with that. Often, though, people will do one more thing. They'll take one more step on the solution. This wouldn't be required in an exam situation, but this is often how people do it. So they'll often factor out an e to the kt out of the terms in the denominator, and that gives a 1600 divided by c plus e to the minus kt. Another way of thinking about that is just divide the numerator and the denominator by e to the kt. If you divide the numerator and denominator by e to the kt, then some e to the kts cancel out and we get an e to the minus kt. So this is an alternative. These are equivalent, but people usually prefer this one because there's one preferred because there's just one exponential in there. So it's a little bit simpler to analyze or graph or think about or look at limits or things like that. Yeah, so there we go. That's the first part. That's solving the differential equation. We're going to do videos for the rest of the parts separately.